Hi friends, this is Maths Swam, and today we are going to start with calculus. Calculus is a broad field in mathematics. There are two further subcategories in calculus. First is differential calculus. Second one is integral calculus. Well, right now we are just focusing on this differential calculus. So let's start. Differential calculus just deals with this instant. Now what is an instant? It is the shortest time period which you can imagine. Maybe 0.0000001 second or even smaller. Now let's take an example. Suppose this is a race, say 10-kilometer race. A runner starts from here, he reaches midway, then he has completed 3/4 of the race. His speed won't be the same throughout. So we'll draw his velocity time graph. Velocity time. So let's plot some points. When he begins, his speed would be just 0. So this is our first point. Then he would increase his speed. That is, he would accelerate, but not uniformly. Then his speed would be constant for some time, a bit constant. Then when about he's say about 3/4 of the race is completed, he would begin to feel tired, and he would then decelerate like this. So that's somewhat the graph for a runner. You must have learned in physics that the slope of a velocity time graph gives the acceleration. Till now you must have encountered some straight line graphs such as this. Velocity time, this angle was 60 degrees, say. So his acceleration would be just, you say, tan 60. This is tangent. Oh, what's this? This is tangent 60 degrees. Tangent 60. That is equal to root 3. So his acceleration was just root 3. Now what's the slope for a curved line? We can discuss average slope. Here's how we do it. Suppose this is a graph of an arbitrary function. Let this be our first point, this be our second point. The average slope between these is the slope of this line. That is the tangent of this angle. This point is now here, so the slope of this line. This is here, the slope of this line. But what is the slope at this point? At this instantaneous point. That is where limits come in. So let's discuss some limits, and then we'll come to the instantaneous velocity again. Now what is a limit? Limit is like, the notation is like this. We can write it as, if x goes closer and closer to A, then y moves closer and closer to B. So we need to make x closer and closer and closer to A, but not exactly A. Here x is not equal to A, but x is as close to as A as it can be. So we'll check it out graphically how this works. Suppose this is a function, an arbitrary one, and this is our A. So the f at A would be somewhat here. This is, say, B. So as x, this is our first x, so the corresponding value of the function would be somewhat here. This is not as close to B. Now I switch colors. I bring this closer to A, somewhat here. Then I take the value of the function. This is fairly near. So I mark these by red dots. So as x, that is this purple dot, moves closer to a, this dot moves closer to b. So the limit can be written as the limit as x approaches what? A. Yes, a. Then y approaches, or we can write function approaches what? B. Yeah. So this is the notation for this limit. Now we'll use limits to find the instantaneous acceleration in that graph which we saw earlier, like this it was. And you know that the slope is rise over run. That is delta y by delta x. So the slope, average slope would be, say this one would be delta y over delta x. And here delta y is just delta v. So average acceleration, we write it like this. Average acceleration is delta v over delta t. And the instantaneous acceleration, that is a, is it's a limit, remember. So the limit as delta t approaches 0 of delta v by delta t is equals to instantaneous acceleration. So try to understand a bit. Delta t approaches 0. So this t just becomes 0, or it approaches 0. It does not actually become 0. Yeah, that's the concept. This is not equal to 0. This is just as close as it can be. Say 0.000000001 second, or even smaller. So this becomes an instant, and the change in velocity in an instant is the instantaneous acceleration. So here we have defined the instantaneous acceleration, the limit as delta t approaches 0 of delta v over delta t. This is a very important concept. In the same way we can define instantaneous velocity, we'll just substitute this delta v for delta s or delta x. Now we'd start with some limits. Suppose I define a function that has, say it is in two parts. This is x when x is greater than 0, and this is minus x when x is less than 0. Oh, I think I should define this again. The function of x, this is the x when x is greater than 0. X is greater than 0. This is minus x when x is less than 0, and this is 6 when x is equals to 0. So we'll try to graph this out here. That now we are drawing in the positive. In the positive x, our function is equals to x, so y is equals to x, and you know that this is a straight line, that is the angle bisector of the two axes. So this at 0 is not 0, this is actually 6. See, this is 6, so this is here. And when we draw this in the negative half also, then we get to know that x is equals to y is equals to minus x. So that is another straight line here. So this is also the angle bisector of these axes. This is also the angle bisector. This is somewhat like a modulus function, but it is not 0 when x is 0, it is 6. So I draw this again properly. So that is a weird function. You can say there's an empty dot, and this is at 6. Now we'll check the limit the limit as x approaches 0 of the function. And you remember the function, don't the function was x when x is greater than 0, minus x when x is less than 0, and 6 when x is equals to 0. So if this function was continuous, then we know that if we shifted this x towards 0, first y would be here, then here, then here, and eventually the answer would also be 0. But this is not a continuous function. At 0 the value is 6. So we have two answers and we need to know which one is correct, 6 or 0, and we know only one is correct though. So we now proceed. X approaches 0, but x is not equals to 0. So we are not concerned about what value y has when x is 0. We are concerned about y when x is just about 0. Say 0.001 or 0.0001. Then you can see with the graph that this just approaches 0. We can zoom in and then see here, this is say very small. Then this would be like this graph, not at 0. At 0 I leave an empty dot. When I may shift this point further this side, I'm shifting this side, so I'll get, say, this line after some time and even smaller lines. So the answer would not be 6, as we don't have to make x equal to 0. X is just approaching 0. So when x approaches 0, we can see y also approaches 0. So our answer is 0. We'll do the rest in the future videos. Thank you and take care till then.